Hi, and welcome to another Dante tutorial. This time, I'll demonstrate how to model a low-pressure carburization and a high-pressure gas quenching using ANSYS and Dante with a simple sliced ring model. To do this, I'll go through creating a carburization model, a thermal model, and a stress model. To start, I'll open the ANSYS workbench, and I'll open the Extensions tab and click Manage Extensions, making sure that DANTE ACT is checked. Next, I'll go to Units, and then Unit Systems, making sure Metric with kilograms is checked. Drag and drop a mechanical model from the component systems into the project schematic. I'll rename it Geometry and Mesh. Right-click Geometry and click Import Geometry and Browse. Find the ring slice 3deg.xt file in the Dante files. If you don't have that downloaded, I also included a download link in the description. Then double-click the model to open it. Once inside, click Face Selection, and while holding Control, select the 4 outer side faces. Right-click in the workspace and select Create Name Selection, and name it Exposed Surfaces. Select Units in the Home tab, and make sure it's set to millimeters, degrees, rads, and Celsius. Now let's define the meshing parameters. Select Mesh in the project tree, and modify it based on this table. To capture the steep carbon gradients that develop during the low-pressure carburizing process, fine surface layer elements are used. In general, it is recommended to use around 20 to 30 microns for element thickness in the carburized case for LPC models. Once you've entered the information, right-click Mesh and go to Insert, Sizing, and set the geometry to one body and set the element size to 1.5 millimeters. Next, to finish the model setup, right-click Mesh and then Generate Mesh before closing ANSYS. Save the project from here. I'll name it LPC Ring Slice Tutorial. Next, we'll move on to setting up the carburization model. Start by dragging and dropping a transient thermal analysis system onto the project schematic. Rename it Carburization Model, and then connect the model from the geometry mesh to the carburization model. Right-click and update it, and then double-click to open ANSYS Mechanical. Quickly check the units to make sure they match what we set before. Click on the Dante model and select Carburization. Click Initial Temperature in the model tree and set it to 0.001. Open the provided LPC Recipe Excel file and select and copy the step end time data column. Select Analysis Settings and click in the first cell under End Time under the tabular data and paste the data there. In the Graph section, click on Step 1, and while holding the Shift key, click on the last step, number 24. It should say multi-step in the analysis settings, meaning you're editing the parameters of every step. Now change the following. Set auto time stepping to on, defined by time, initial time step to zero point zero 0.01, minimum time step to 0.00001, maximum time step to 75 seconds, and set nonlinear formulation to full. Now let's assign the material. Select material in the Dante toolbar, and then select the yellow box next to the geometry, and select the whole body. Hit apply, and then for this tutorial, I'll select the S93XX material, and then change the carbon weight fraction to 0.001 to simulate AI SI 9310 material. Select carburization temperature in the Dante toolbar, and in the details, click tabular data. Add 2 rows and set the total time to 0 and 50,000 seconds, while the temperature should be 950 degrees Celsius for both, and then click apply. Next, I'll add the model control from the Dante tab, keep the max carbon change per substep as default of 0.0005. Next, add an output frequency from the Dante toolbar and click tabular data. I'll keep it default, which is 10 substeps per step. Next, I'll enter in the LPC boundary conditions. Under environment, add a convection step. In the details, change the following: scoping method to name selection to an exposed surface, film coefficient to a constant value of 0.005, and ambient temperature to a constant of 0.014. Lastly, go to the tabular data, and while holding Control, select every diffuse step, which will be every even step not including 0. Right-click and deactivate these steps. And with that, the carburization model is finished. Now all we have to do is click Finalize Model Settings in the Dante tab, save it, and then right-click Solution to solve. Once the model is done solving, you can view results by going under Dante Results and selecting Carbon Right-click Carbon and then evaluate all results. Click Write Carbon Profile from the Dante tab. In the details, I'll change the name to Sliced Ring CC under Save Data, and then evaluate all results to write out the carbon profile. This will be used in the other models in this tutorial. Save your progress, and then I'll close ANSYS Mechanical to get started on the thermal model. Now that we're back in the ANSYS workbench, I'll drag and drop a transient thermal analysis system into the project schematic and rename it Thermal Model. Drag and drop the model from the ring slice model to the thermal model, and then right click and update it. Then open ANSYS Mechanical by double clicking Model. Make sure to check that the units are correct before getting started. Go to Dante Model and select Thermal, and then set the initial temperature in the project tree to 20 degrees Celsius. Go to the analysis settings and change the information to match this table. Make sure to set the number of steps to 6 and start at step 6, working backwards as the values must be added from highest to lowest. In addition to the numbers, the following must also be set: auto time stepping to on, defined by time, carry over time stepped off, initial time step to 0.01, and minimum time step to 0.00001, time integration on, and nonlinear formulation to full. Next, I'm going to assign the material. Select Material in the Dante tab, and then click the yellow box next to Geometry, selecting the part body and clicking Apply. Again, select S93XX as a material, and then change the carbon to 0.001. Next, define the control file by clicking Model Control in the Dante tab. Click Kinetics Mode Table, and then set Step 5 and 6 to -6 to allow tempering of martensite, and click Apply. Add an output frequency from the Dante toolbar and click Tabular Data. For this tutorial, I'll leave the values as default and click Apply. Now I'll move on to creating the thermal boundary conditions. Add four convections from the Environment toolbar and rename them to Heating, Quench, Cool, and Temper. For heating, set the scoping method to name selection and choose exposed surfaces. Set the ambient temperature to 950 degrees Celsius and expand the film coefficient and choose tabular. Right click and deactivate all steps except the first. Expand independent variable and select temperature. For coefficient type, select surface temperature, and in the tabular data, enter 20 degrees Celsius and a convection coefficient of 0.00005. And for the second line, 1000 degrees Celsius for 0.0012. Moving on to quench, set the scoping method to name selection and then choose exposed surfaces. Set the film coefficient to 0.0032 and the ambient temperature to tabular data. Set edit for data to ambient temperature, and while holding control, select all steps except steps 2 and 3. Right click to disable the other steps. Go to the bottom of the tabular data and add the following information to the time and temperature tables. Next, for the cool step, set the scoping method to name selection and again choose exposed surfaces. Set the film coefficient to 0.0001 and set the ambient temperature to 20 degrees Celsius. Deactivate every step except step 4 and 6. Lastly, for the temper step, again set the scoping method to name selection and choose exposed surfaces. Set the film coefficient to 0.0001 and set the ambient temperature to 180 degrees Celsius. In the tabular data, deactivate every step except step 5. Next, I'll add a CN profile from the Dante tab and set the number of carburization profiles to 1. In the carburization file, navigate to the Dante files and then select the carbon profile you created earlier. Under Carburization Activation table, click Tabular Data and activate Step 2 and click Apply. Now we can finalize model settings, save the model, and right-click the solutions and solve. Once the model is done running, go to Dante Results and choose Total Hardness and then evaluate all results. Save the project and exit back to ANSYS Workbench. Now, onto the stress model. Add a static structural analysis system to the project schematic and rename it stress model. Connect the model from the sliced ring to the stress model and the solution from the thermal model to the setup in the stress model. Uptape and then double click to open ANSYS Mechanical. Again, make sure to check that the units are correct before getting started. Go to the Dante tab and click on Dante Model and select Stress. Click Static Structural in the project tree and change the environment temperature to 20 degrees Celsius. Select Analysis Settings and just like before, enter in this information into the details, making sure to work backwards from step 6. select Material from the Dante tab and select Part Body for the geometry. Again, select S93XX as the material and change the total carbon to 0.001. Add a model control from the Dante tab and click Kinetics Node Table. For step 5 and 6, set it to -6, rate dependent, and click Apply. Add an output frequency from the Dante tab and click Tabular Data. Again, I'll leave this as default of 10 and click Apply. Add the CN profile from the Dante tab and set the number of carburization profiles to 1. Again, we're going to click Carburization Files and select the same CBN file. Under Carburization Activation Table, click Tabular Data and activate Step 2 and click Apply. Expand Imported Load in the project tree and select Imported Body Temperature. In the details, set the source time to all and right-click Imported Body Temperature and select Import Load. From the Environment toolbar, add a frictionless support and displacement to the project tree. In the details of frictionless support, click the yellow box next to geometry and select the 2 internal faces of the ring slice and click Apply. The frictional support allows the part to slide along these planes, and the displacement boundary condition prevents the part from sliding longitudinally or vertically while allowing the part to shrink and grow thermally. In the details of displacement, click the yellow box next to geometry and select the bottom left vertex and click Apply. Set the Y component to 0. Now we're ready to run the stress model. Add a finalize model settings from the Dante tab and save your progress before right-clicking solution and solving. Once the model has finished running, right-click solution and select Insert Stress and Normal. In the details of normal stress, leave the default orientation for the x-axis signifying radial stress. Right-click Normal Stress and select Evaluate All Results. And this concludes another Dante tutorial. If you have any questions, feel free to comment down below or send us a message at support@dantesolutions.com. Thank you for watching and happy simulating.